Hello students, you are welcome to today's lecture on electric charge and electric field. Way back at the start of this course, we have covered topics such as oscillatory motion, waves and sound, which are definitely things we can look around us and experience every day. But if we look around at our modern technological world, there is actually one aspect of the universe that seems to be being used more than any other, and that is electricity. In terms of transport, lighting, eating, cooking, communication, so much of what we do and how we interact with the world is based on electricity. So, in this study session, we are going to be dealing with whole range aspects that deal with electricity and its closely associated phenomenon, that is magnetism. The learning outcome for this study session: when you have studied this session, you should be able to discuss static electricity and charge, describe conductors and insulators, state Coulomb's law, explain electric field and field lines, discuss the relationship between conductors and electric field in static equilibrium, and at the end you should be able to discuss application of electrostatics. Now let's start with electric charge and static electricity. What is electric charge? Electric charge is defined as the property of matter that causes an object to experience a force when it is near other electrically charged objects. Basically, there are two types of electric charge, which are positive and negative electric charge. In fact, those labels, that is positive and negative, were given to the electric phenomenon by the very famous American inventor and scientist known as Benjamin Franklin. An example of electric charge: two ebonite rods, when rubbed with force, exert a force of repulsion on each other because they both carry negative charges. Also, when two glass rods are rubbed with silk, they tend to repel one another because the two glasses carry the same charges, that is positive charge. However, the ebonite rod, which has been rubbed with force, tends to attract the glass rod, which has been rubbed with silk, when they come in contact, because the two objects now carries different charges. So now let us talk on what a static electricity is. Static electricity is a form of electric charge that is typically produced by friction, and this form of electric charge causes sparks or crackling or the attraction of dust or air. Example of static electricity: for example, if you rub your shoes as you walk along the carpet, you might experience build-up charges in your body. If you touch a door handle or someone else, you might see a small electric spark. This spark is as a result of the stored charges on your body. So you should be cautious of the static electricity, especially in dry climates, in order to avoid electric shock. Now let us talk about laws of electric charge, conservation of electric charge. Just like positive and negative numbers can cancel out, positive and negative charges can do the same thing. In fact, it turns out that everything in the universe is essentially composed of positive and negative charges, but essentially in equal amounts. So for example, yourself, you are composed of a whole bunch of electric charges. You don't feel terribly strong electric forces most of the time because your positive and negative charges are exactly balanced. So this universally obeyed law of nature, called the law of conservation of charge. Just like law of conservation of energy, law of conservation of charge states that the total amount of charge is constant in any system. The amount of charge is constant in any system. Now let's talk about insulator and conductors. On the basis of charge conduction, substances are broadly classified as either conductor or insulator. Some substances, such as metals like iron nail and salty water, allow charges to move through them with relative ease. This free electron can move through the material, such as air, moves through loose sand. So any substance that has free electrons and allow charge to move freely through it is called a conductor. On the other hand, insulators are substances that do not allow charges to move through them. An example of these are glass cup and conduit pipe used for protecting electrical wires at home. As you can see from this slide, you can see an example of an insulator and conductor. Now we move to Coulomb's law. As you have already known that like charges repel while unlike charges attract. Whenever we talk about attraction and repulsion, it means that there is a force that is attracting an object or there is a force that is repelling an object. Now I will talk about the force, and the force is nothing but an electric force. To talk about electric force, we shall consider a special law called Coulomb's law. This law is named after a French scientist known as Charles Coulomb. The law states that the force F between 2 point charges Q1 and Q2, separated by a distance r, varies inversely proportional to the square of the distance r between the two charges. And this force is also directly proportional to the product of the two charges, and it acts along the line joining the two charges together, and the force is repulsive when we have the same charges, and it is attractive when the two charges are opposite to each other. Mathematically, the force F can be represented as F equals to K multiplied by Q1 Q2 divided by R squared, where K is constant and approximately equals to 9.00 times 10 raised to the power 9 Newton meters square per Coulomb square for free space, that is for a vacuum medium. The epsilon naught is called permittivity of free space. Now let's take an example on Coulomb's law. Now suppose the Coulomb's force between two charges Q1 and Q2 separated by distance r is F. If the separation between the two charges is now tripled while the magnitude of the charges still remain constant, then what will the value of the new Coulomb's force be? In this case, since we have been given in the question that r is equal to 3 times the original distance between the two forces, which is r, so the new Coulomb force will become F new equals to K Q1 Q2 divided by square of the new distance, which is 3r squared. So our F new will now be equals to K Q1 Q2 divided by 9r squared, since 3r squared is also equals to 9r squared. So in this case, if F is equals to K Q1 Q2 divided by r squared, therefore the new Coulomb force will now be equals to 1/9 of the original force. Haven't walked through this example 1, you can now test your knowledge of understanding of Coulomb's law by answering the question on the next slide. Be prepared to discuss your answer in the discussion forum. The exercise: two charges each of 5.0 times 10 to the power minus 9 coulombs are separated by a distance of 1.5 meters. Calculate the magnitude of the Coulomb force between the two charges.